Hi, I'm Dr. Justin Essery of Rice University, and today we're going to be talking about learning about the world using simple Bayesian models. This is the second week of Poli-Sci 506 Bayesian statistics. The objective of Bayesian analysis, as I have written on the screen here, is to learn about characteristics of the world by combining the prior evidence, I should say prior information, prior beliefs that we have about some state of the world, with evidence that we collect in a rational way. That's the point of Bayesian analysis, and we talked a lot about that last week when we were talking about basic concepts of Bayesian inference. This week I want to show a lot of examples of how this works in a kind of applied scenario. I'm going to show examples in four different four different areas, four different arenas. One of them has to do with binomial probabilities, events that are either 1 or 0, something like flipping a coin and it coming up head or tail. Count data, which is exactly what it sounds like, data that are composed of counts of events. So for example, things like in political science, things like battle deaths are often recorded as counts, the number of deaths. They can only take on values 0 or more, and they have to take on discrete whole number values from 0 up. We're also going to look at simple means and variances. I'm going to give a couple of, one example of how we would learn about simple means. So you have a prior belief about what the mean of some variable is and what its variance is, and we update that using the evidence we've collected. And finally, we're going to look at linear relationships, so-called Bayesian regressions. These are what a lot of political scientists and other social scientists are sort of the bread and butter model that we think about, trying to relate y to a linear continuous y to x using a linear model. And there's a slope and y-intercept associated with that, thinking about a single variable model here. We might have prior beliefs about what the slope should be based on previous work. And then we collect evidence and update our beliefs about that. So right now I'm going to show you all four of these examples, and I'll talk a little bit about the theory behind it, and then we'll do some example work in R. So let's get started. All right, so I'm going to start off talking about applying Bayesian models to binomial events. So as I have here, a binomial event is just an event, x, that's either 0 or 1, that occurs with some probability. Usually theta is thought of as PR x equals 1, and that probability, by the laws of probability, has to be between 0 and 1. I'm going to observe a certain number of these outcomes. So for example, we might observe the number of elections where a Republican incumbent wins. We might observe, for example, the number of times a head or a coin comes up heads. Anything where there are two possibilities, they're mutually exclusive and exhaustive, and there's some probability that one of the two events happens, can be characterized as a binomial event. Now, I've written Bayes' rule again here. I'm only going to write this one example, but it applies for all of the different data sets or all the different data structures, rather, we're going to look at today. Bayes' rule just says that our posterior belief about the parameter theta, given the data, is going to be the ratio of the likelihood of the data set, given theta, times the prior belief we have about theta, divided by this normalizing constant, which is the probability of the data really integrated over theta. I've written it as a discrete sum here, but probably it'd be more appropriate to write that as an integral if theta is continuous, which in this case it is. The normalizing constant here is typically not going to be something we spend a lot of time thinking about, though. The reason being, all we need to know is that the posterior is proportional to some value. It's proportional in this case to the numerator of that earlier expression, Bayes' rule. And as long as we can get the shape of this proportional function, we can always move up or down the values of those functions so that they sum to 1, they integrate to 1, the way that you really would expect a continuous distribution to do. So we need the integral of f of theta given the data to equal 1 by, again, a law of probability that less than 1 or greater than 1 would sort of imply that they're not this is not a probability density. But whatever this numerator here is, we can always multiply it by some appropriate constant in order to make this true. So the upshot is we don't spend a lot of time thinking about what this value is. We typically neglect it because we can figure it out based on what we discover about the numerator here. Well, let me give you an example of how that works. And it's going to come up pretty much right away in our example of binomial data sets. So the likelihood of a particular binomial data set, a series of election or outcomes, or perhaps a series of coin flip dispositions, head or tail, is determined by the binomial likelihood function here. All right, so the binomial likelihood function is just the binomial coefficient times theta to the k, where remember theta is the probability that x equals 1 in this case. I think we're using x as our binomial variable. 1 minus theta, so probability x is 0 to the power of n minus k. K is the number of positive, or actually I should say x equals 1 outcomes. Change that to x. And n minus k is the number of x equals 0 outcomes. So what this is the joint probability of us observing, for example, k heads and n minus k many tails if we were to flip a coin n many times. N minus k, which is the binomial coefficient, tells us how many possible combinations of binomial events can produce a pattern of k successes. So, for example, if I flip a coin 3 times, there are many different ways I can end up with 2 heads. I can end up with the head the first time and the last time. I can end up with a head the first 2 times, and so on. Binomial coefficient aggregates all of those possibilities so that they're all accounted for when we calculate the likelihood, because each one of those is an independent event and they all have independent probabilities. We don't really need that, though, because this coefficient is just going to be a fixed number, and it will be subsumed in the constant term. So going back up here, it's going to be just a constant term that ends up in this denominator. So we don't actually need it when we go forward with analysis, at least not until the very end. And you'll see what I mean when we go to R. All right, so conjugate priors we talked about last week. A conjugate prior is just going to make the analysis a little bit easier, because if you go back to Bayes' rule here, if the likelihood, which is right here, and if prior are conjugate, that means that their product is going to be a analytically closed and solvable density of some kind, a parametric density. And in this case, if we want conjugacy of the prior in the binomial likelihood, we want to use the beta distribution. So the beta distribution has this kind of ugly looking constant that precedes it that involves gamma functions. Again, we can pretty much ignore that as a part of our sampling process or any of our other Bayesian analysis process. It's just going to be subsumed in the constant term in the denominator. What we really care about are these things. This is that's going to actually enter into our function. You can see it looks a lot like the binomial likelihood, which is not a mistake. Alpha and beta are hyperparameters, so-called hyperparameters in this function, and they indicate in the prior the number of observed successes and failures that are in some ways captured in the prior. So, for example, I might have prior beliefs about the probability that I flip a coin and it comes up heads that are based on all the coins that I've seen up to this point, or maybe just my beliefs about this particular coin that I developed somehow. And if I believed it that this coin was fair, I might say alpha is 5 and beta is 5, which would indicate that I have prior beliefs that are centered on an equal probable outcome. In other words, a 50% chance of x equals head and a 50% chance of x equals tail. And the fact that each one of them is 5 indicates that I believe that, but I don't really believe that. It's not as though I've seen thousands of successes and failures and they're equally divided. We could play with those parameters to change the outcome if we wanted. The important thing, of course, is that whatever prior you set, it reflects your prior belief, your actual prior belief. So you may want to plot the prior a bit to make sure that the visual representation of that prior matches what you qualitatively believe your prior beliefs to be before you get started with your analysis. Anyway, once you've decided what your priors ought to be, the final posterior is going to be the proportional to the product of the prior and the likelihood. And you can see, because the prior and likelihood are conjugate, these things sort of enter in real nicely. Alpha and beta rather, just become sort of like additional counts of outcomes that just go right into the exponential part of the likelihood, just as though we had observed extra outcomes in our data set. So there's a really intuitive interpretation of the prior in this particular case. It's literally as though I'd observed a bunch of extra heads or tails, or perhaps election outcomes, a bunch of extra Republican and Democratic wins, if this is the United States. Right, so that's really all we need to know. There is one additional thing I want to talk about. One could opt to use a so-called flat prior. A flat prior implies that we don't know anything about theta before we conduct our experiment. So if you think about an informative prior might have some belief about theta that is concentrated. It obviously has to be bounded between 0 and 1, just like the probability. An informative prior might say, well, I know something about how likely it is, and perhaps I'm thinking this is a fair coin if it's a coin flip, so I'm going to center it on a half, and I've got some kind of distribution around that, whatever. A flat prior, by contrast, tries to communicate no information. And so a flat prior might say, well, let me just do this right here. Every value of theta between 0 and 1 is equally likely. At least before my experiment, I believe that every one of them is equally likely. Before I observe any data, I believe that they're all equally likely. If that's the situation I find myself in, I can simply, if I want to, enter the posterior as the likelihood. The answer you're going to get is obviously going to be uninformed by any prior. It's not the prior is entering as a constant. And in fact, in this case, typically what's going to happen is that the Bayesian result is going to be very similar in some ways to the maximum likelihood result. So probably what's going to happen here is my estimate of theta is the sort of highest, the modal theta in my posterior density is going to be equivalent to the maximum likelihood result I would get if I took this likelihood function and calculated the maximum likelihood of my sample using MLE. So I think that's enough theory for now. Let's go to R and take a look at how this would actually, how we could estimate theta using priors and data. All right, so let's take a look at some binomial data. I'm going to generate this data as a Monte Carlo process instead of using real data, because the advantage is we'll actually know the right answer. We're going to learn about some process, but we can tell whether we're learning correctly or not, because we happen to know the right answer already. So what I'm going to do is I'm going to clear my data set, which is already clear my R memory file rather, and I'm going to set a seed so that you at home can replicate this exactly the way I have. And I'm going to set a prior number of successes and failures at 5 each. So this is equivalent to this is the alpha and beta from the prior distribution that we talked about earlier. Then what I'm going to do is I'm going to draw 200 values of a binomial variable x from a binomial distribution with probability 20% of a success. So there's a 20% chance that x equals 1. Notice that this does not necessarily provide a good match to our prior expectation, which is roughly 50%. Actually, really, it's 50%, centered on 50% probability that x equals 1 with some degree of variation around that estimate. Our likelihood, well, the actual data generating process that we created does not provide a good match to that expectation. And I'm doing that to show you how the data can update your beliefs based on what you see happening sort of in your experiment or in your data set or whatever. So the first thing I'm going to do is I'm going to sample out of the posterior, which has a closed form, and the form that it has is the beta density. So if I go back to my let's see here. If I go back to my original lecture file here, you'll see the posterior, which is right here, takes the form of a beta density, which looks a lot like a binomial, with these alpha and beta parameters included. What I'm going to do is I'm going to put in alpha and beta equal to the sum of x equals 1 successes that I saw in my data set, plus my alpha prior parameter minus 1. And that matches exactly what I expected to see before. So I should see, here we go, here's my posterior. You should see I should have k plus alpha minus 1 in the exponent of the first term, where k is the number of successes, alpha minus 1 is my prior parameter. And in fact, I have that. Same thing for the shape, the second parameter, the so-called beta parameter. That's going to be the sum of failures, x equals 0, plus beta, which is my prior parameter for the number of failures, minus 1. So if I just draw a ton, I'm drawing 10,000 samples out of this posterior distribution, I'm going to get a pretty good sense of what my prior beliefs ought to be based on the quasi-experiment that I ran and my prior beliefs. Here we go. So this is a histogram of the draws that I just calculated. And you can see it's centered roughly on slightly lower than 22, 25, somewhere between 20 and 25%. Now I drew this data out of a distribution that had 20% probability of success, yet my posterior belief is centered not over 20%, but over something like 24, 23%, something like that. In fact, if I really wanted to find out post-samp, it's 24%. There we go. That's my mean expectation. That's my mean posterior belief. Yeah, there we go. Why is that? Why isn't it over 20%? Well, the answer is because my prior information was providing some degree of influence over my conclusions. Let me show you what I mean by this. So what I'm going to do is I'm going to put a curve on this histogram that's the theoretical probability density that I have available to me. I have this available to me, the analytical form of the posterior, because the prior was conjugate. And that's going to make it possible for me to exactly plot out what the posterior should look like. Normally, or I shouldn't say normally, but quite often that we don't have that luxury. We must rely on sampling out of a distribution in order to draw inferences about what that distribution looks like. In this case, I can do both. So you can see that the sampling procedure and the drawing the function procedure end up producing similar results. And that's not a mistake that I'm doing that, because we're not going to have recourse to the drawing the distribution technique for very much longer in this course. These things get pretty complicated pretty fast. Anyway, I'm going to just draw the posterior function from 0.1 to something like 0.4. And I just plot the value of the posterior using the d beta function. So I should step back here a minute in case I think I skated over that point. R beta draws random numbers out of the beta density. R beta, there it is. And you can see there are the two shape parameters and whatnot. The d beta plots the density function for the beta. So if I just essentially plug in all my candidate theta values from 0.1 to 0.4 into the density and then plot them, overplot them on my histogram. Oh, I must have missed something. Let's try that again. There we go. You can see that my histogram is a very close match to the underlying true value of the density. And again, that is not a mistake. Sampling is a way of learning about distributions. We're going to avail ourselves of that a lot later. This is just to give you some sort of intuitive notion that the two results produce similar outcomes. Okay, so that's a posterior with our informative prior. It's roughly 50% chance of a head, 50% chance of a tail. Now, what happens if I were to impose a totally flat prior? So now I'm saying I don't know anything. Every value between theta equals 0 and theta equals 1 are all equally probable. All I'm going to do is remove this stuff right here. That's my prior parameters. I'm going to remove those from my posterior. So in essence, all I'm going to do is just plot a likelihood. I'm going to treat the likelihood as if it contains all the information I need to learn about theta, the probability that this coin or whatever I'm looking at here comes up heads. So if I do that in blue, you'll see that it tends to be shifted closer to the true value of 0.2 that we drew the data from. Now you might be thinking, well, wait a minute. If you're getting closer to the truth without the prior, why are we calculating a prior? Or why are we including a prior? Well, of course, first of all, if our prior is accurate, or at least somewhat accurate, if it contains genuine information, then it's not only probable, but almost, well, I'd say it's probable that the prior is going to help us get closer to the true value. So the first thing to say to that is, well, if we actually have information and it's decent information, we ought to put that into our analysis process in order to gain the benefit from that. Secondly, when the information is not accurate, yes, it's true, we're going to sort of suffer the consequences of that. But as the sample size of our data set here gets very, very large, the prior is going to be overwhelmed by the information contained in the data anyway. So all I've done here is just increase my experiment from 200 flips of a coin to 2,000 flips of a coin. And if I do that and just repeat my whole thing over again, it looks like they didn't quite, hold on, perhaps I should shrink this down a little bit. So 100. All I did was I'm blowing up the density sizes so that they look better. Yeah, still too big. Maybe cut that down to 50. Try it again. Yeah, there we go. That looks pretty good. So now I'm going to replot everything again. And there we go. What you can see is that now the prior and posterior densities are much closer. In fact, that's kind of jagged. I don't really like that. Let's increase that a little bit. Yeah, that's nice and smooth. So all again. And that's fine. So what we can see here is that the more information we add through the data set, the more similar the prior informed and prior uninformed results get. And again, that's not a mistake. That's consistent with the Bayesian idea that you start with some particular belief and you update according to the amount and quality of information you have. The more information that you get through evidence, the more it informs your eventual outcome. I also, just to sort of play around this a little bit, suppose we actually set the prior to be accurate. So instead of saying 5 successes and 5 failures, what if we set a 20% success rate? So what would that mean? Well, we could start with, let's see, it would be 1 in 4. So yeah, 1 out of 5, 20% successes. Maybe we say we've actually observed a few more of those, 2 and 8. And then we cut the, we'll just leave it at 2,000. Now what's going to happen is probably, they're going to be very, very close to one another. Now, suppose I had much less data. Suppose I only had, let's do a little more than 20. Let's say I had 50 observations. Now, if I go back and do this analysis, remember the blue is the prior informed result, the red is the posterior take that back. The blue is the data only result, no prior. The red includes information added by the prior. The red result is actually looking pretty good. It's looking better, in fact, than our sort of raw data result. Let me expand that up a little bit so it's a little bit clearer for you to see. Try her again. Yeah, not quite. Oh, that's probably too high, but we'll find out. No, it keeps. There we go. I just drew samples, so it was the right scale. Anyway, so you can see that the prior informed result, which is red, is really nicely centered over 0.02. The posterior result that does not include prior information kind of moves around more. And if we do this over and over again, you might see it moves around a little more than the prior informed result. The prior informed result tends to stay centered over the right answer of 0.2, a little more reliably. So this is just a way of saying if you add good information to an analysis, it will make the analysis better. So there's nothing really magic about priors, nor is it cheating. It reflects the fact that you don't come to the evidence with no information. You come to it with some information, and then it rationally integrates that information into the evidence that you've had. I just want to say one more thing here. I can count if I want to calculate the mean. So mean estimate. Mean estimate. I can just calculate the mean of the samples I drew, which in this case is giving me a mean prediction in the posterior of about 21%, I would say, 20.5%, which is pretty close to the right answer. There's an analytical solution for that mean prediction if I wanted to obtain it, but I have the samples and I can calculate the mean of those samples quite easily, and that answer actually is going to be pretty accurate, as we'll see later when we talk about learning about Bayesian posteriors with sampling. I can also calculate the variance of that estimate by just calculating the variance of the posterior samples that I drew. In this case, it's looking at standard error of about 0.05, 5%. One last thing before I go, or before I return to turn over to the count data analysis. You'll notice I changed the sample size that I was drawing out of. I first started with 200, then I did a really giant one. Now I'm down to just 50 samples. But I always, or 50 observations in my data set. But I always drew 10,000 samples from the posterior density. There's an important distinction here between the number of data points you have, which is just determined by your sample, and the number of draws from the posterior distribution you use to make conclusions about what the posterior looks like. Regardless of how big or small your sample might be, you should always draw lots and lots of samples from your posterior. And we'll talk more about this when we talk about sampling as a methodology in following weeks. But I'm not making up data here. The only point of drawing those samples is just to basically give me lots of smooth information about what the shape of this posterior looks like. So you should always draw many samples, regardless of how big. You should always draw many samples from your posterior if you're going to use sampling as a method of learning about your posterior, regardless of how big or small the data set that you're working with might be. Okay. Well, now let's take a look at, that's all I have to say about binomial data. Let's take a look at count data. All right, now let's talk about count data. So count data comes in the form x as starting at 0 all the way up to infinity in any discrete number inside that set. Things like I said before, battle deaths, for example, is something that's intrinsically a count data. You can't have half a death. You can't have negative deaths. When we have data like this, we might want to know the cumulative and probability densities of the number of events that will, the count of things that will occur. So if we're trying to predict the deadliness of a conflict, we might operationalize that with the number of battle deaths. And consequently, we want to know something about how many we would expect under various circumstances, and what's the uncertainty around that, how much variation is there from conflict to conflict, and so on. So as you might know from working with count data in the past, count data can be modeled with the Poisson distribution, which is going to serve as our likelihood in this case. The Poisson likelihood is, I've listed it here, it's an exponential type function. Key points here are we have n many observations, each one of which is a count. So like, for example, n many conflicts, each of which has a count of battle deaths in it. And then S is the sum over all observations of all the counts. So that could be a very large number depending on exactly how much data you have. The mean of the Poisson is lambda, and we're going to try to use data to learn about lambda. So what if we want to form a conjugate prior to be able to have an analytically closed posterior density of counts? Well, we can use the gamma density. This is the gamma density. Once more, looks a lot like a Poisson. It's not a mistake. We've got some prior parameters here, A and B. A, it corresponds to the prior sum of counts that we have observed. And B is the prior number of events. So B is playing the role of how many events did we see occur, and A is what was the total number of, total count rather, of all events inside each one of those distinct observations. This bit here, which involves a gamma function, just like before, that's a constant. It's going to be subsumed into the prior. We don't need to worry about it when we're conducting an analysis. We can always just correct for it. And so this is the posterior that is formed by a combination of the prior and the likelihood. And again, it's a gamma function. Looks like a Poisson because it's very similar to a Poisson. And it involves combining S, which is the sum of all the counts in all our events from the data set, and A, which is our corresponding prior sum of counts that we specified. And again, N plus B plays the role, sort of fills in for N being the number of counts that we've observed, and B is the number of events rather, that we add as a part of our prior. So pretty straightforward, very similar in structure to the binomial data set, although we are using different likelihoods and priors. Now we can take that information and go to R and see what happens when we calculate posterior densities using real data and generated data and priors. All right, so now we're looking at count data. I'm going to clear out all the stuff I had from the binomial data set earlier and start looking at the count data I'm going to generate. Once again, I'm going to set the seed so that if you're repeating the script at home, you get the same answer as I do. And I'm going to set the number of counts to 100 and the sample of size to 10. What this means is I am acting as if I have observed in the past 100 counts, 10 different events that sum up to a total of 100 observed events, a count of 100. So that can vary in terms of how that happens. For example, that could be all 10 events have a count of 10. That could be one of them has 100 and the rest all have 0, although that's quite unlikely. But that's what I'm acting as though that's the information I am embedding into my prior, as though I've observed that. And that effectively means I'm assuming, on average, about 10 a count of 10 events will occur per observation. Now I'm going to generate the data out of the R Poisson density, and just take a look at that here. The Poisson distribution is exactly what it sounds like. The R Pois means I'm drawing observations out of that. And I'm using lambda, which is the mean or intensity parameter or whatever it's called, but it is the mean. I'm setting a mean of 6. What this means is I am undershooting my prior. So I was assuming in the prior I was going to see about a count of 10 events per observation, but I'm actually going to see about 6. So once again, for illustrative purposes, I've set up the prior to be as though it's a little inaccurate, somewhat inaccurate, although not terribly inaccurate. So S is the sum of all counts inside my 200 observations. It's a big number. And I'm going to draw a bunch of observations out of the gamma density, which is the form of the posterior, as I showed it to you a moment ago. One thing you'll want to watch out for is that in this case, the scale parameter is equivalent to 1 over the parameter that's found in the lecture. It's also found in Simon Jackman's book, which is this course uses. R, for whatever reason, uses 1 over that as its scale parameter. It's fine. You just need to be aware of it. Otherwise, your results will be crazy. And then if I just plot the densities, or really just plot the distribution of all the draws I just took from that gamma density with here's my data and my prior right there. And down here I've got my data. No, that's the data, 200 observations. and the prior right there. That's B. This is what I get. I get a distribution for my belief about lambda, the mean, that's between 6.2 and 6.4. And once again, if I'd like to, I can just calculate that mean. It's about 6.3. I was almost exactly right. So a little higher than the data would suggest, which is again consistent with the fact that our prior was indicating a much higher lambda, a much higher mean number of events per observation. Once again, I can plot that's the analytical form of the posterior density, which, because we used a conjugate prior, we know it. And it pretty closely matches the samples that we drew out of that distribution, which is, again, not a mistake. And then I can compare my result using the informative prior to what I would get with a flat prior, so a totally uninformative prior. And so what I'm going to do is just set A and B to 0 and let the data completely inform my result. And what I get is what I expect. The data are telling me that the mean count of events per observation is basically 6, very close to 6. The prior is what's inflating that to some degree. Just like with the binomial example that we did earlier, if I had more observations, these things would be closer. If my prior were a little more accurate, my prior informed answers would be a little more accurate as well. And again, the point of this is just to illustrate that Bayesian analysis takes prior information, combines it with evidence, and produces a posterior density. So if I want to calculate that's my posterior informed estimate of the mean number of observation or count of observations count of events per observation that I should expect given my experience with this data. And if I wanted to, I could calculate a variance or that expectation. Maybe a standard deviation would be a little more informative. Standard deviation is about 0.17. So I'm looking at 6.3 plus or minus about 0.3 many events per observation based on my prior and my data. All right. Now let's take a look at continuous events, or continuous variables. That is to say, variables that are sort of range from negative infinity to infinity and everything in between. All right. So now we're going to talk about continuous data, and I've annotated or denoted this variable, this continuous variable, as y, ranging from negative infinity to infinity with an average value of mu and we're going to start with a known standard deviation of sigma. Now, it is the case that in most instances we cannot presume that we know sigma. We estimate sigma. Uncertainty about our estimate of sigma really ought to be propagating up into uncertainty in our estimate of mu, which you can see if you look at the likelihood here. Mu and sigma are sort of intrinsically sort of intertwined in this likelihood, and so uncertainty in one might affect. If we undershoot the sigma, we might overshoot the mu, and vice versa. For now, I'm going to treat the estimate of sigma as God, as gospel. So in other words, I assume it's correct and indubitable. That's not the best approach to take, and in the homework for this week, if you're actually taking my class, you'll explore a scenario where you allow for uncertainty in sigma to propagate into the estimate of mu. But regardless, we're going to proceed with this example right now, assuming sigma is known. So the likelihood is just, in this case, something most statistical people I'm sure are familiar with, the good old normal density. The likelihood is just the probability of observing a particular y given mu and sigma under the normal. So we're saying, if I've got some mu here, then my probability of observing some particular y is, in essence, proportional to the distance of that y from the purported mean. It's as simple as that. And the bigger the standard deviation is, the flatter that curve will appear, and so the more likelihood that events far from the mean will get. This is an easy one in terms of finding a conjugate prior. It's the normal. So if we want to have a density that's conjugate with a normal likelihood, you use a normal prior. And that also means it's pretty easy to think about for most of people with some data experience. You just specify a mean and a sigma that correspond to your beliefs about mean and sigma prior to this experiment, or this data set, observing this data set or whatever. And so the posterior is just proportional to a normal density with a particular mean and sigma, mu and sigma. And these things correspond, actually this should be sigma squared. There we go. Oh, come on, you. There we go. I should have kept it sigma. Oh, whatever. Anyway, what was I saying? Right. So the in order to calculate the posterior analytically, you enter these things in for mu and sigma into a standard normal density, and you can see that it's a little bit unclear. I should note y bar here is the average observation. It's the empirical mean, the average observation of y in the sample you have. So I'll just write that down. Y bar equals sample average y. And because we're considering sigma squared to be fixed and known, where is it? This guy here. So this sigma squared is actually the sample variance of y. We're just taking it from the sample, estimating it, and presuming it's known. That appears at several points in that formula. For example, it appears right there as well. If you enter in, but anyway, as I was saying, the mean and sigma squared for this posterior density, you can see are in some sense averages of the prior and the likelihood. Now, I'm doing a bit of abuse to the term average because it's by no means an actual average, but it sort of adds together those two bits of information and combines them into a whole. And actually, we're about to go to R. You'll see how that prior information informs the eventual result you get when you try to draw inferences about mu, the mean, posterior mean, based on data and your prior beliefs. So let's take a look at what that looks like in R. All right. So now what we're going to do is take a look at this continuous data set. And what I've done, I'm going to clear out my old data set here, set the seed once again so results are replicable. I'm going to set a prior mean of 12 and a prior sample standard deviation or prior standard deviation of y of 0.5. Then I'm going to draw 200 observations, and actually I just realized I should set that to n since I went ahead and made n a parameter here. I'm going to draw 200 observations from the normal density that has a true mean of 5 and a sample standard deviation of 1. That's much smaller in mean than my prior belief, but a little bit more variable than I was expecting. So I won't, you can look at the notes if you want to sort of look at these computations here. They just correspond to mu and sigma star, just like we calculated, or just like is listed on that sheet, on this class notes rather. The terms are all there. I don't feel like belaboring them. Then I'm going to draw 10,000 samples out of the posterior with mu star and sigma star specified as the Bayesian analysis would indicate, and then take a look at what we have. And what do we have? Well, the result is centered on about 5.1, and in fact we could, if we wanted to, we could. Our posterior mean estimate, this is a little bit weird. Our posterior belief about the mean is, no, our mean posterior belief about the mean is 5.13, about 5.13, a little bit above the 5 out of which the data were generated, which is consistent with our idea that the prior put a lot of weight on a much higher value. I can analytically calculate the posterior. There it is. That's my posterior belief density about the mean of y. This, or actually, I guess I called it x in this particular example. The mean of x, I guess, in this case. And I didn't do this, but if I wanted to see what the density would look like in the event that I did not use Bayesian, well, rather, I said a flat prior would be the best way to put it. All I have to do is just say, okay, I want to use the data information. So I'm going to set standard deviation equal to the standard deviation of the data I have. And I'm going to set the mean equal to the sample mean of the data I have. And then I'm going to plot the resulting line in blue. And interestingly, this looks a lot more diffuse than our posterior belief was. Additionally, it appears as though wait a minute. Right, of course. So we're calculating the standard deviation of the mean, not the standard deviation of a sample x. So we have to divide by n-1 in order to get the sample standard deviation of the mean without the prior information. And what you see here is that the main effect of the prior is sort of spread out the uncertainty about our knowledge of the mean based on the data. And in fact, if we were to repeat this whole sampling process over and over, not using the seed, what you'd see is the posterior informed result, the prior informed result rather, tends to stay pretty static and pretty centered over about 5.1, no matter we sort of draw this data sets over and over again. By contrast, the simple, actually it looks like, yeah, the data are pretty reliably coming out between 5.1 and 5.2. I actually take that back. It looks like what's happening is it's just the prior information, all it's doing is just kind of spreading out our beliefs about the data a little more. And actually, generally speaking, even though looks like it's a bit more variable, it does tend to put more weight on 5.0, which is the true value, which is kind of interesting given how uninformative our prior beliefs were. Well, anyway, it's kind of interesting. Right, so we could calculate the mean, and we could also calculate the standard deviation of our beliefs about the mean by looking at the standard deviation of post-samp. And so if I combine these two together, it looks like based on, actually that would include, let's go back to our original result so that with the seed, so we get exactly the number we had to begin with. Our posterior, the mean posterior belief about the mean that generates this data, the mean to the normal, is 5.12, standard deviation of about 0.7, so we're looking at a 95% confidence interval of 5.1, somewhere between plus or minus 0.12, roughly, which does actually cover, just barely, covers the true value. Well, anyway, those are some pretty basic examples. We did the binomial example, we did the count example, we did the example here with continuous data. Now let's talk about a little more complex, probably more useful example of Bayesian regression, where we're looking at the relationship between usually two continuous variables, y and x, sometimes a continuous variable and a binary or categorical, some other independent variable. Let's take a look at that. Now, the idea of a conjugate prior is much more important when we get to more complicated forms of analysis, such as linear regression. So I'm going to talk a little bit about regression in the linear context and how a conjugate prior can help us specify information in the prior that leads to a nice closed form posterior. So what do we want to do in a regression? Well, we're trying to model data with a line and then draw some kind of inference about beta coefficients or slopes, dy, dx's, and maybe also about sigma squared, or the degree of noise present in the data generating process, the standard deviation of the regression, so-called. So I can run a standard regression analysis using LM or GLM in R, or using regressance data. That's going to give me information about the likelihood. In other words, the probability of the data given various values of beta and sigma squared. But I need to have a prior if I want to form a posterior belief in using Bayes' rule. This can get very, very complicated if we've got lots of different x variables that are going into our regression, and they're all related to each other in some way. So it'd be really nice if we could find a conjugate prior that allowed us to easily specify all of our prior beliefs about what beta and sigma squared look like, then allow us to integrate that with the data information and produce a sort of understandable, easy to comprehend posterior. And in fact, there is a way to do that. So what we're going to do is say, okay, the posterior probability of beta given sigma squared y and x is the normal density. The idea here is we're assuming as part of this analysis the classical linear normal regression model, which is to say that the error in the relationship between y and x is normally distributed. That leads us to conclude that through various central, actually you don't really need that, you can still appeal to central limit theorems to get this result. Anyway, the density of beta is itself going to be normal, and that density is going to have parameter beta 1 and as a mean, and a standard deviation or a VCV matrix sigma of the estimated sigma squared times b1. Now, little b1 and big B1 are going to be themselves products of prior and likelihood information, which you'll see in a second. So what are our priors here? What are our priors about beta, and what are our priors about sigma squared? Well, actually, before I get to that point, let me step back a little bit and continue to talk about the posteriors here. So the posterior density of sigma squared is given by the inverse gamma function, which you may not have heard of. It's a particular distribution. R knows what the inverse gamma is, and we'll talk about it in a second. And this has two parameters. I believe it's a shape and a dispersion parameter given by these functions here. And the marginal density of beta given y and x, which is to say factoring out uncertainty in sigma squared, is given by a t density with a shape beta 1, centrality parameter, or how do I put this? A centrality parameter beta 1, a dispersion parameter sigma 1 squared beta 1, and a degrees of freedom v1. Now, I've been referring to these quantities b1, cap b1, or big B1, v1. What are all these things? Well, these are all combinations of prior and posterior information. The bottom line is you choose four things. First, you choose a vector of prior means for the regression, one for each parameter. So you say, okay, I'm running regression with 4 variables and a constant. That's 5 total elements in the regression. I need to figure out what's my prior mean for each of one of those things. That's fine. That mean is going to be normally distributed. So in other words, that's going to be the mean of a normal distribution. I also need to specify a k by k matrix that's the prior VCV of beta. So what I do is I basically say I'm going to specify a prior for beta which is a normal. And it's going to have a mean beta 0 and a VCV of a mean of B0 and a VCV of cap B0. I also need to specify some prior information about sigma squared, which is the basically the amount of error, the level of error contained in this data generating process. One of those parameters is V0, which is the degrees of freedom for the prior. Another one of those parameters is sigma 0 squared. Now, what these two things add up to is they give you, when combined, the sum of squared errors for the prior regression that we're sort of running as a fictitious idea. Basically, what this tells us is how much the sigma squared parameter says how much dispersion is there in the how much dispersion do I think there is in the data generating process before I conduct this particular analysis, and the V0 parameter tells me how sort of certain am I, how many fictitious trials have I run? How big is my fictitious data set? How committed am I to this prior? The smaller that number is, the less committed I am to this prior. So if I specify these four things, this beta 0 and cat beta 0 as a, and actually I should sort of probably note this, these form a prior density for the beta, oops, as a normal centered around beta 0 with sigma of cat beta 0. Then I need to, so that's what these things turn into. And then I need to specify two things for the sigma for the dispersion. I need to specify v0 and sigma 0 squared. These give me a prior density for sigma squared. What am I doing here? And that prior density is the inverse gamma function with location parameter v0 and dispersion parameter sigma squared 0 times v0. Right. So what this allows me to do is then say, okay, if I specify a normal density prior for beta and I specify an inverse gamma prior for sigma squared, I can take these things, combine them with the results of my regression. You can see I've got X transpose X here, which is the model matrix for my particular regression, which we'll talk about in a second. Here's beta hat, which is the product of the regression. I've got somewhere down here, S, the sum of squared errors from the regression, which is the measure of the variance. R, which is just this matrix product here, which is full of products from the regression. I can sort of run this through a bunch of formulas and I can produce known analytically fixed posterior densities for the regression that are understandable. And in particular, that closed form posterior density for beta, this will be the multivariate t density. So, which you might recognize, since the t density is also the density that beta takes even when the prior in a frequentist analysis, or equivalently when the prior is flat or improper. So regression is a pretty complicated technique, and we can integrate prior beliefs into the regression analysis if we in advance say, well, we're going to limit our prior density to take a certain form. We're going to say our prior density for beta is going to take a multivariate normal form. Our prior density for the dispersion parameter sigma squared is going to take an inverse gamma form. And if I restrict myself to those prior densities, I'm going to be able to combine that information with the likelihood products to form a posterior density that is sort of relatively easy to work with, namely the t. So let's see an example of how this works in R. So now I'm going to conduct a Bayesian regression analysis on some fake data. You can see I'm clearing out my memory and making some fake data out of the data generating process, 2x plus 0.05 plus a normally distributed error term. And I'm binding the independent variables and the constant into an X matrix because you saw in the write-up there that we need X transpose X for some of these products, and so eventually we're gonna need X transpose X. I'm going to run a model, GLM model of y given x, and so if I do a summary of that linear model, you can see that I'm recovering pretty close to the true values of beta. 0.05 or 0.5 for the intercept is pretty close to 0.47, our estimate here, and 2.14 is pretty close to 2, which is the true value of the estimate. Nevertheless, that's where frequentist analysis would end. I would just look at the estimates, I would look at the standard errors, and I'd be done with it. So I'm going to recover the coefficients, VCV, and residuals from this linear model using the appropriate functions. Now what I want to do is say I want to generate posterior densities for my beta coefficients given a prior, which means I need to actually specify priors. Okay, that's fine. I'm going to use the conjugate priors that we just discussed. So I'm going to say, I'm going to specify that in advance of this analysis, I believe that both the intercept and the x coefficients had a mean of 0. So I'm just calling that B0 because that's what it was in the write-up. I'm also calling it coefs prior. It's the same thing. And these are going to be related to one another in a multivariate normal distribution, and they're both going to have standard deviation of 0.25 and variance 0.25 and covariance of 0. So in other words, the prior is going to be such that these two coefficients are completely uncorrelated with one another. Now, you can see what my prior density looks like if you plot it out using the multivariate normal library here. So what I'm going to do is, for all betas between -3 and 3, I'm going to show you what the density looks like. And so I've created a little matrix here that's going to hold my PDF values. I'm just going to cycle through all my different values of beta from -3 to 3. And I'm going to compute the density of the multivariate normal at the intercept, or I'm sorry, it's the x coefficient comes first, I believe. The x coefficient and for the intercept. And the mean of this is going to be equal to the mean of the prior, and the variance covariance matrix is going to be equal to the VCV of the prior. So I'm going to compute all these values. Should only take a second. Then I'm going to create a contour plot. Now I'll show you what it looks like first. Here's a contour plot. What this is every circle in the plot gives you a it's the line of constant density. So for example, this line at 0.05 tells you these are all the different values of the beta coefficients for which the density is 0.05. And you can see it climbs a mountain here. This is basically a mountain centered on 0, 0 with no correlation between the two coefficients. I could also use a filled contour plot, which is a little bit more attractive, and I think I need to expand this out a little bit so it looks right. And I'm going to actually specify that the colors be gray so that you get a little bit better view here. And I might even turn up the number of nope. Divided by 40. Yeah, it's actually not enough gradations. Maybe we'll go down to 10. Oops. Yep, not enough. There we go. So what we're doing is the same thing as the contour plot. We're just sort of shading in values for which the density is various numbers of values here. So the density is 0.6 when the color is really black here, and you can see that the value of highest density is right around both the coefficients being 0. The density falls off as you get further from 0, and in fact, once you get past about 0.1, there's hardly any density at all to be computed. So this is a visual depiction of, in fact, maybe I should zoom in on this a little bit and maybe go from -1 to 1. Show you this again. There we go. Looks a little better zoomed in. This is this is an expression of my prior beliefs. I think that the betas are basically 0. I think that they're not correlated with one another. And I'm pretty certain, actually, that they're 0 in the sense that most of my density is concentrated around 0, and there's some degree of uncertainty around them. Now, I could make these densities wider. So, for example, I could go back from -3 to 3 here, and I could change my variance instead of being 0.25 to being 0.5, for example. Oh, and now I need those additional levels of gray in here. There we go. You can see that now my density is spread out a little bit. And in fact, if I turn up my variance even higher, oh, ran out of gray, so I need to turn that up even more. So the reason I'm having to increase the number of colors in the plot is because I'm getting more and more gradations of the prior density that I have to account for. And so you can see now my prior is getting more and more and more diffuse because I've just put in more and more diffusion in my prior beliefs. So now I'm less certain about where these betas are in advance. So that's what my prior looks like for beta. I can just write it down and specify it. What about my prior for the error, the degree of variance in the data generating process, or sigma? Well, I'm going to specify VO is 2 and sigma 0 is 1. Now, what does that look like? Probably much easier to see this by depicting the inverse gamma distribution. So you can take a look at d-inv gamma, which is the density of the inverse gamma distribution. It's available in the MC-MC-Pack package here. And I'm going to plot this from 0 to 3. Now, sigma squared can't be less than 0 because that would imply 0 would imply no variation, no error in the data generating process. Negative numbers have no interpretation. And there are two parameters I've specified, the shape and the scale. The scale is V0 times sigma 0 over 2. The shape is V0 times 2. And if I plot this out, that's my prior over sigma squared. My maximum value is, I think it's about a half, but I have a great deal of uncertainty about where sigma lies. I could change this if I like. I could, for example, change the V0 parameter to be 20. What that's going to do is it's going to really crunch in my prior here. So it's going to center it much more on 1. It's going to make me much more certain about what the parameter is. Remember, V0 is the sort of the number of trials I run, or the number of data points, quote unquote, in my prior. I'm going to leave this fairly diffuse because I don't have any strong convictions about the level of error in this data generating process. In fact, because I created it, I know that it's 1, but I wouldn't have known that if I hadn't specified the data generating process in advance. Okay, so now all I need to do is take this prior information and compute all of the quantities that are given as formulae in this case in the Jackman book. So all I need to do is compute little b1, cat b1, v1, v1, sigma 1 squared, the sum squared errors for the regression, and r, and then I can create a student's t-density using those things that will give me my posterior density for beta given y and x. So if I go into R here, all this code, all this is just literally copying and pasting things from Jackman's book into R and computing the quantities. So now I know that my marginal posterior density for a beta coefficient on x is going to be given by the multivariate t density with certain parameters as given in the Jackman book. So what I'm going to do here is call the mnorm_t library. I'm going to plot my posterior density from -6 to 6. And what I'm going to do is for each possible combination of intercept and x coefficient parameters, I'm going to calculate the multivariate t density for each one of them, centered around a mean of b1, which is one of those quantities we calculated from the Jackman book, and setting s equal to, again, some quantity from the Jackman book, df equal to v1 here. And then I'm going to use a filled contour plot to depict this. This will take just a second to run. And here we go. Here's our posterior density for the intercept and the beta coefficient, and intercept and the x coefficient rather. And we can tell, again, from summary of the linear model, 2 is the x coefficient. You can see here, this is the x coefficient right here. It's centered on 2, but there's a great deal of uncertainty here. The intercept is centered on about a half. That makes sense, but again, there's a great deal of uncertainty. And my beliefs about where the x coefficient is are related to my beliefs on the intercept. In other words, these are correlated. If I think that I happen to have a very high estimate of the intercept, so for example, if I want to assess my belief, for example, that the intercept is equal to 2, that's going to be, generally speaking, related to a very low belief on the x coefficient. Conversely, if I think that I've got a low value on the intercept, I'm going to conclude that I have a very high intercept on the x coefficient. So beliefs about these two parameters are actually related to one another, and they're related to one another in particular through both the VCV and the prior information. Now, in my case, I specified that in the prior, I had no belief that these two coefficients were related at all. So in this case, all of the correlation is coming. It's coming specifically through the VCV matrix. Now, I could simply show this, or I could zoom it out, maybe make the picture a little nicer, and show this and say, here's my posterior belief density, whatever, go to it. But it's a little bit difficult to interpret. And one thing I might want to do, for example, is say, well, I want to just look at the posterior density of one particular coefficient. In this case, I want to look at the posterior density maybe of the x coefficient, which is the second element in this vector here. So it turns out that, and this is given in the Jackman book, let me scroll back here. If I wanted to know the marginal density of just one particular value, so for example, if I wanted to know what's the density of just, for example, the x coefficient given y and x, that's going to be given by the multivariate t, student's t distribution with the non-centrality parameter equal to beta 1 for this particular x value, the dispersion parameter equal to sigma 1 squared beta 1 for that particular x value, and degrees of freedom equal to v1. So what I can do, going back to my R plot here, I can say, well, I just want to pull out the second value of this posterior vector here, and I want to just focus on the second entry in its VCV matrix, and I want to plot the density of this x beta like so. It's actually, I'm just going to focus on the posterior here for a moment. This is my posterior density around beta x, so the relationship between x and y. And as you can see, it's near 2, but it's sort of shifted a little bit to the left. That reflects the fact that in the prior, I thought the relationship was 0 with some kind of certainty. In fact, if I plot that prior on here, so I'm just plotting my prior here as a line, you can see that it was very dispersed but centered way over here off to the left of the graph on 0. And that prior is kind of pulling my estimate over to the left towards 0, which makes sense because I went in believing it was 0. Suppose I had went in believing that it was actually a positive, or suppose I went in believing that it was 1. So I'm just going to go back and change my prior and redo all of this analysis, assuming now that my prior density was 1. So this will take a little second to run. Okay, now you can see the prior density is centered over 1, and the posterior is actually shifted closer to 2. It's almost perfectly centered on 2. That makes sense. I went into this analysis thinking that the beta was positive, or about 1, and my data not only confirmed that, but confirmed that it was a little bigger than I thought. So my posterior density was actually closer to the so-called maximum likelihood estimate of a coefficient around 2. That makes sense. And again, you can see how different ideas in the prior can change my results. So now with these formulas, you can get a sense of, okay, how do prior information and likelihood information in the data set combine to form my posterior beliefs, which is really great. And in addition, it allows me to say this density, this posterior density, is my belief about beta given the data. I don't have to make any confusing statements about likelihood. I don't have to say, p-values or this complicated interpretation. I can just say very straightforward things. In fact, when we get into Bayesian hypothesis testing, we'll see that it's a much more straightforward way of presenting evidence. Let's just talk about that right now.